Thank you, Professor Sacco, for your kind introduction. Ladies and gentlemen, good morning. My name is Camilla Ronchei, and I am a research assistant at the University of Parma. First of all, I really would like to thank all my co-authors. The goal of the paper is to thoroughly investigate the mechanical properties and the fracture toughness of a pervious concrete with a design porosity of 15% by performing an extensive experimental campaign. My presentation consists of the following section: introduction on the pervious concrete in the civil engineering applications, presentation of the employed raw materials and then specimen preparation, description of the experimental mechanical test performed on PC specimens, presentation of results and discussion, and the final conclusions. Nowadays, the use of pervious concrete, also named PC, as a pavement material in low-volume road applications represents a best management practice to mitigate the problem of stormwater runoff. As a matter of fact, PC allows rainfall to be drained and to percolate through the concrete to the subgrade materials, thus reducing the stormwater runoff and at the same time recharging the groundwater. Many studies of literature have also identified the potential of PC in the removal of heavy metals, which are considered the most critical pollutants found in stormwater runoff due to toxicity, non-degradability, and bioaccumulation. In particular, both the fundamental component of PC, that is cement paste and aggregates, have the individual capacity to remove heavy metals by precipitation and absorption. The distinct feature of PC is the limitation of the fine aggregate content in the mixed design. Thus, PC hardens into a high porous material with a high degree of interconnected and tortuous pores in size between 1 to 5 millimeters, where the pore formation is supported by narrowly graded coarse aggregates, which hinders the dense packaging of the mixture. The porosity of a typical PC varies in the range between 15 to 25%. However, as is well known, the presence of pores inside the mixture negatively affects the strength of the concrete. Therefore, the aim of the present research work is to thoroughly investigate the mechanical and the fracture behavior of a PC for civil application, especially in the context of road pavements, with the purpose to extend the PC use to high-volume road applications. First of all, I would like to show you the experimental campaign performed at the laboratory of the University of Parma. The raw materials employed for the specimen preparation are limestone Portland cement, natural aggregate, tap water, and an additive. The cement is a 42.5 SN2ALL characterized by Portland clinker and the limestone percentages in the range between 18 to 94% and 6 to 20% respectively. The natural aggregate is a granite gravel with a particle size between 5 to 22 millimeters. In order to obtain a design porosity of PC equal to 15%, the particle size distribution of aggregate is the one shown in the figure on the right-hand side. Finally, the additive is a polycarboxylate superplasticizer consisting in an antipathic surfactant with 30% of solid content. The mixed proportion employed for specimen preparation is determined by using the so-called unit volume method and by assuming a water cement ratio of 0.25 and a PC design porosity of 15%. The mixture proportion obtained are those reported in the present table. Subsequently, cement and aggregate are put in a concrete mixer, are mixed together for about 90 seconds, and then water and additive are slowly added, and the concrete mixture is mixed until its surface attains a metallic cluster. Then molds, characterized by different sheets depending on the mechanical test, are filled with the concrete mixture and are compacted with a manual roller. The specimens are cured in laboratory for about 24 hours under normal climatic conditions, and after the molding, the specimens are submerged in water at room temperature for 28 days. The mechanical properties and the structural toughness are experimentally investigated after about 28 days of curing. The compressive strength FC is determined by performing compression testing complying with the present UNI and standard. The 5 tested specimens are cubes with the nominal geometrical sizes recorded in this figure, and each test is performed until failure under load control by using an electromechanical press. The flexural strength FCF is determined by performing 3-point bending test according to the present Union standard. The 3 tested specimens are prismed with the nominal geometrical sizes reported in the figure, and each test is carried out to failure under load control by using the universal testing machine instrument. The flexural strength is then computed as a function of the peak load and the specimen sizes according to the present equation. Elastic modulus and the fracture toughness are finally investigated by performing 3-point bending test on edge-notched specimens according to the modified two-parameter model proposed in the past by Vantadori and co-workers. In particular, the 5 tested specimens are prismed with a notch in the lower part of the needle cross-section and with the nominal geometrical sizes reported in this figure. Each test is carried out under crack mount opening displacement control by employing a clip gauge, and the applied load is measured by means of a press. In particular, each specimen is monotonically loaded up to the peak load, and when the peak load is equal to about 95%, the specimen is finally unloaded under load control. Then the specimen is finally preloaded up to failure under mode control. At the end of each test, we compute the angle between the loading direction and the crack path, that is the crack kinking angle theta, according to the modified version of the two-parameter model, in order to take into account the possible crack deflection, even if a remote mode of loading is applied. Finally, by exploiting the experimental measurements in terms of peak load, crack kinking angle, and the initial compliances and unloading compliances, we can compute the elastic modulus and the factor toughness according to the formulation of the modified two-parameter model. The computed values in terms of compressive strength FSC related to all tested specimens are recorded in this table, and the resulting mean value is equal to about 15 megapascal with a standard deviation of 6 megapascal. Such a value is in agreement with that obtained by you and co-workers, which have investigated the compressive behavior of a PC with a design porosity of 20%, obtaining a mean value of the compressive strength equal to 18 megapascal. Regarding the specimen fracture, it can be observed that the fracture surfaces are quite flat. Thus, failures usually occur both in the aggregate and in the cement paste between aggregates. As a matter of fact, under compressive loading, all the points on the same plane of the PC are stressed at the same time, and the cement paste usually breaks first due to the small bonding interface. Then, when the cement paste breaks, a part of the stress is transferred to the lower plane, whereas another part is absorbed by the aggregate, leading to the failure. The present cars, in terms of load against the cross-head displacement, are related to the 3 tested specimens under 3-point bending loading. It can be observed that the scatter of the experimental cars is quite narrow, and the mean value of the peak load is equal to about 5.7 kilonewton, with a low value of the standard deviation equal to 0.06 kilonewton. The computed value of the flexural strength, FC, for each specimen is reported in the present table, and the mean value of the flexural strength is equal to about 2.6 megapascal. Regarding the fracture surfaces, it can be observed that the cracks usually propagate through the pores. However, some crushed aggregate sections can be observed, as for instance this one in the 2PC specimen. Regarding the fracture test, the experimental curves in terms of load against the crack mount opening displacement are recorded in these figures, and it can be observed that the curves, both in the peak stage and in the unloading reloading stage are quite dispersed among themselves. Probably this behavior is due to the large force which are randomly distributed into the concrete mixture, does play a fundamental role in the propagation of cracks during the post-peak stage. Moreover, it can be observed that the initial slope and also the trend of the softening branch are quite similar among the tested specimens. These figures show the front and back sides of the fracture zone of each tested specimen. In particular, it can be observed that the cracks usually start from the notch tip, except for one of the two sides of the 4PC specimen. The computed values of the crack kinking angle theta are reported in these figures, and it is important to highlight that when cracks are not plane, the mean value of theta is computed by averaging the theta values related to the back and front sides of the specimen. In the analyzed specimens, the theta value ranges between 10 degrees to 47 degrees, and the most significant crack deflections are observed in specimen 4PC and 5PC. This behavior can be attributed to both large pores and small bonding interfaces located near the notch tip, thus influencing the crack initiation. Then usually cracks propagate in an irregular manner with a continuous change of direction, and the cracks tend to follow the orientation of both aggregates and pores along their entire path. Moreover, it is interesting to highlight that also the failure of some aggregates is observed. Finally, the experimental results in terms of peak load, initial compliance, unloading compliance, and kinking angle are reported in the present table for all the tested specimens. Moreover, also the computed value of the elastic modulus and the fracture toughness are listed in this table. It can be observed that the computed value of elastic fractures and of elastic modulus and fracture toughness are not dispersed, as demonstrated by the low values of the standard deviation. According to the knowledge of the present authors, research available in the literature related to the fracture behavior of PC are very limited. The present results are compared with those obtained by Chan and co-workers, which have investigated the fracture behavior of a PC with a design porosity ranging between 15 to 25%. And the employed aggregate was a granite gravel with a maximum particle size equal to 10 millimeters. The author obtained a fracture toughness mean value equal to about 0.33 megapascal times meters to the power of 0.5, which is in line with that obtained in the present research work. So now let us move to the conclusions. In the present paper, we have investigated the mechanical properties and the fracture toughness of a pervious concrete with a design porosity of 15% by performing an extensive experimental campaign. On the basis of the obtained results, we can conclude that the mean value of the compressed strength equal to about 15 megapascal is in agreement with that obtained by you and co-workers. The mean value of the flexural strength is equal to about 2.6 megapascal, and the obtained results are not dispersed as demonstrated by the low standard deviation value. The fracture surfaces related to fracture tests demonstrated that the cracks, usually starting from the notch tip, are characterized by deflected paths due to both large pores embedded in the cementitious matrix and small bonding interface between aggregates. Consequently, mixed mode regime occurs at the crack tip even if a remote poor mode one loading is applied during the test. Finally, the mean value of the fracture toughness is equal to about 0.46 megapascal times meters to the power of 0.5, and such a value is in line with that obtained by Chen and co-workers, thus confirming the correctness of the experimental campaign being performed. Thank you for your attention.